A novel non-linearity of matrix exponentiation performs better with less parameters on periodic data, determinant prediction, and is competitive on Sci-Fi 10 with 20 times less parameters. So today I'm reading Intelligent Matrix Exponentiation. It's from August 10th, 2020. It's from Google Research, Thomas Fischbacher, Moritz Fisching, Julia Komsa, Versani, Potempa, Alakuijala. So this paper proposes a new non-linearity, which is made up of several matrix addition, multiplications, but most importantly of matrix exponentiation. They are able to prove Lipschitz bounds for to prove robustness, which is, I think, it's not possible with other non-linearities. They show that it has a universal approximation property. Also, what's interesting about this nonlinearity is that thanks to the exponential there, they can approximate periodic functions and multivariate polynomials very well, which is not possible with ReLU. They show this also on this spiral approximation on approximation, for example, functions that look like sinus. It also performs competitively on general purpose, compared to general purpose networks on Sci-Fi 10, but it has about 20 times less parameters. So same result with 20 times less parameters. I'm not sure if this is going to be a breakthrough, but I think what's important about this paper is that maybe you can, in many cases, you can optimize your architecture by using non-linearity that is related to your problem. And if you are trying to fit a periodical function, maybe you should consider non-linearity that it will help you with that. And as well, if you are trying to predict determinants of matrices, for example, again, maybe you should have different non-linearity to achieve optimal performance. Yeah, I think that's the main contribution. So in classical nonlinearities, usually we combine only through summations, but that means that on some kinds of problems, you will have to have much more layers than you would have if you've chosen the right nonlinearity. It seems, yeah. So the proposal here is to have higher dimensional nonlinear function from m-dimensional space to n-dimensional space, and this nonlinearity is combination of summation, multiplication of matrices, and application of exponential. There were previous attempts to do something to find sort of new activation functions, higher dimensionals. None of them very much that successful. There are these capsule networks as well. I don't think they are used that much these days just yet. Perhaps they were not. Yeah. In particular, there's this neural ordinary differential equations node and their arithmetic expansion ANODE. That have received attention, and I think they are I think down there we will find out that they are state of the art on the problem of non-convolutional architecture for Sci-Fi, not Sci-Fi. I think Sci-Fi maybe as well, but also MNIST. Okay, so what is the architecture, right? So exponential of a square matrix is defined via Taylor expansion like this. So there's basically summation of some sort of weighted summation of powers of the matrix, where the powers are actually multiplications of matrices. It's not element-wise powers. And so they define this specific layer, which they call M layer. In their equations, they often use this Einstein summation. That means that if you don't have some kind, one of the indices, if it's not present on the left, it means that it's being summed over on the right. So what they define here is that they have this x as an input. They have x and y as the coordinates. Then they have a channel. You can think of this that all these three could potentially disappear if you would actually flatten the image and have just one channel. So that's basically, you could almost see this as a vector. Then you have a matrix multiplication over that vector, and then you have I think there's a after that you have another second multiplication. I'm not sure why there are two multiplications here, but then you have a bias, and you sum. In the end, you do lots of these summations, right? We have this Einstein summations. So here we go. X is first projected to d-dimensional latent feature embedding space by U. Then 3-index tensor maps each such latent feature to n times n matrix. Finally, a Bayes matrix is added to the feature-weighted sum of matrices. The result is matrix indexed by row and column indexes J and K. Well, I can see that this is a preprint, right? So yeah, on the left here they should have J and K, and so we don't actually sum here over J and K, right? So they have, there's a bug in this. Okay. And then the output is that we take this M, we apply exponential functions on it, a function that was described here as this summation of the powers of M, and we do another matrix multiplication and another bias. It's trained conventionally, minimizing closed functions such as L2 or cross-interpret with softmax, using backpropagation through matrix exponentiation. So the interesting fact about this M layer is that it is able to generate arbitrary exponential polynomial combination of its features. That means that on these kind of problems where exponentials and polynomials are sort of, we are trying to fit these, then this should perform better. Or I think, I don't actually have a proof of this. So what's also interesting that it is able to, for example, to fit well periodic functions, because consider matrix M, where we have 0 on the diagonal and minus W and W on the cross diagonal. So, and if you do exponent t times M an exponential value of this, you will get actually cosines and sines in a matrix, periodical function of t. There's also connection to Lie groups, which are these differential symmetries in physics. Okay, let's go. So, for example, also this M layer has very nice, interesting visual result here in when they compare this performance on classification of a Swiss roll double spiral, where M layer has these very, very nice straight spirals that it's able to create this kind of beautiful classification, while ReLU has this sort of, it still performs well, but it has this much uglier result, which doesn't sort of generalize beyond available data. Also, it would be interesting to see how many parameters they needed for this Swiss roll. Okay, never mind. Let's go. To enhance training stability and model performance, they do add a Frobenius norm of exponential of M matrix. And that's sort of the simple regularization used. Here there's a demonstration how well they can fit those periodical functions again. As a Swiss roll, they can approximate periodic functions excellently compared to neural networks where in these, which actually, perform very badly when you go to the future. They start to be incapable of extrapolating. Well, basically they cannot extrapolate, right? But this actually is able to extrapolate. So basically machine learning seems to be about this fitting of the functions, and if you select the proper function, basis, proper group, you can get better results, and you can even sort of extrapolate, right? Well, basically, and also depends on the nature of your extrapolation. If you, for example, extrapolate into the future, maybe you would like to include also some group of periodical functions. All right, let's go. Example of functions learned by M-layer and DNN are shown in picture, which illustrates that in contrast to DNN, M-layer is able to extrapolate such functions. Learning determinants. So to demonstrate the ability of M-layer to learn polynomials, we train M-layer and DNN to predict determinants of 3 times 3 or 5 times 5 matrices. So if I understand it correctly, they put on input a matrix and they try to predict the value of its determinant, and they actually show that they perform very well. It's going to be seen on this image. But never mind. Let's look at the sort of standard datasets. So M-layer compared to the best state-of-the-art ANODE, which is non-convolutional ODE architecture, if I understand correctly. How does it perform on MNIST? So on all of the problems, it performs sort of similarly, but it uses generally less parameters, especially compared to the sort of real prelude. It uses much less parameters, but compared to these ODE networks, it's sort of on the same order of magnitude amount of parameters. So I hope you got the basics of the paper, the spice, the juice, and subscribe, and I hope to see you next time. And